All right, in this video, we're going to talk about dissociation of acids, bases, and water. So in the last video, at the very end, I ended with how water can be amphoteric, and so this is going to kind of focus on that a little bit more. All right, so the dissociation of acids and bases. All right, this is by far one of the most important things, and you need to keep this at the forefront of your mind all the time when you read about acids and bases. Acids and bases, only strong acids and bases can dissociate 100%. So earlier in the year, I asked you to memorize the strong acids, and I asked you to memorize the strong bases. You cannot forget them. Okay, so here's a list of the strong acids. Pause it if you need to, write them down, learn them. Here's the strong bases. Remember, it makes the B on the periodic table, so it's group 1 plus hydroxide, right? All of these. And then group 2, barium, strontium, and calcium are here on the periodic table. Okay, so this is group 2, the 3 at the bottom. All right, and so they dissociate 100%. So you can write it like this, where you have acid react with water to give us hydronium and nitrate, or you can write it like this, where it dissociates 100%. All right, I don't care which way you write it. I probably am going to try to write it like this so that there's no confusion, but you can dissociate your acids just like that. Bases, you cannot. Bases, you have to show reacting with water because they need to get a hydrogen from somewhere. All right, so weak bases have to be dissociated with water, and weak acids and bases, they do not dissociate 100%. They exist in equilibrium. So not all of this will turn into this like it will up here. So that changes how we have to find pH and stuff. So this is a really, really, really important concept, and that's why you really have to know these. All right, and I tried to get you to start writing these reactions way back at the beginning of the year. So if you didn't take the time to learn it then, you're going to have to learn it now. All right, so strong acids versus strong base. So if you just look at the left side of the screen, right, and we have the strong acid HA, and it's going to dissociate 100%. So at the very end, we don't have any HA left. It's all turned into H3O and A-. So here is my example reaction, okay? If this is where I start at, then I would have HCl and water separately. And then at equilibrium, I've got chloride ions. Those are the little green ions. And then hydronium ions, H3O ions. And I have one for each one. So every single hydronium has its chloride that it used to be stuck to, the hydrogen that it came from, right? So I have 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5. Okay? So none of this is left in the solution. All right, now if we look at a weak acid, it's only a partial dissociation. So I have here HA. I make a little bit of H3O plus, and I make a little bit of A negative, but I have a crap ton of this stuff left over. So that's equilibrium because it doesn't make any more product, right? So a reaction on this side for this top reaction would be HA plus H2O goes to H3O and A negative, right? Well, I have this, but I also still have some of this left over. So that's equilibrium, okay? So if I look down here on the bottom, I have all of this. So these are the HFs that are left in the, right? It's H and F, 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 H and F. This is H3O. So I made one H3O and I made one F. That's it. Everything else stayed over here. So weak acids dissociate very, very, very little. And every weak acid dissociates to a different amount. It has a different K. All right, so we're going to write the dissociation reactions with water for the following acids or bases. So if HCl dissociates with water, it dissociates 100% because this is a strong acid. So H2O is a base. It's going to take the H and leave behind chloride. All right, and the next one, NH3 is a base. It's a weak base because it's not one of the strong ones. So I use these arrows. Weak bases take hydrogen. All right, now one of the questions that I get asked a lot is how do I know what's an acid or a base? Typically your acids start with H, bases don't, okay? Not only that, but anything that has nitrogen bonded to 3 different things is going to be a base because that nitrogen has this extra lone pair of electrons, and that's where it attaches the H. Okay, so then it looks like that as a conjugate acid. All right, so this is going to be a base, and I know that because I've got nitrogen attached to 2 hydrogens, and it's attached to that C6H5 thing. So C6H5. You don't have to know what that looks like. And I have 2 electrons there. So it can take a hydrogen and attach it right here, right? So that's how I know it's a base. It also doesn't start with H, guys. And it's going to be weak because it's not one of the strong ones. So I'm going to add an H to the end of it and add a positive sign to it. And then it's going to make hydroxide. Okay, this is an acid because it starts with an H. So I make H3O plus acetate. And it's weak. It's not strong. That's why I have the equilibrium arrows. All right, and then this is a base. And since this is a salt, I'm just going to dissociate it. Because it's a base, but it's also a salt, and it's a strong base, right? It just dissociates 100%. All right, this is a weak acid here, even though it has that extra H. So that is like, it looks like this. It has 4 H's on it. So if a nitrogen compound has 4 H's on it, it's not going to gain another one. There's no room for it. Its octet is filled, right? So this, when it reacts with water, is going to give its hydrogen up. Same thing happens with this one because it has that positive charge on it. All right, that's it. So water is amphoteric. It can behave like an acid or a base. So if I look at just water by itself and react it with itself, I get this reaction. So if you have a glass of water, this is happening and it's in equilibrium. Okay. Side note, other substances like HSO3, 1 negative, and H2PO4, 1 negative are also amphoteric because this can go back to phosphoric acid, this can go back to sulfurous acid, and they can also still lose those hydrogens. All right, but back to this water thing. The K that we find for this, because remember these are both liquids, so they don't belong in the K. And we have hydrogen ion and hydroxide ion. Guys, remember this is equivalent to H plus. So H3O plus is the same thing as H plus because it's just water with a hydrogen stuck on it. Okay, so anytime you see those two things, they're the same to each other. So my KW is going to be this times this, no reactant because they're both liquids. And we find that at 25 degrees Celsius, the KW is 1 times 10 to the negative 14. So what I have is H plus times OH is equal to 1 times 10 to the negative 14. And so this can be true in any solution. So if I have H plus, I can find OH. If I have OH, I can find H plus. So it allows us to go back and forth between the two. So if I have a solution with a concentration of H3O plus of 1.5 times 10 to the negative 3, and we want to know the concentration of OH, I can use that equation. And remember the KW value is equal to 1 times 10 to the negative 14 at room temperature. Okay, so this is H plus. So I'm just going to plug that in and solve for OH. And so that's going to be 6.7 times 10 to the negative 2. All right, and then what is the H plus when we have the OH here? So just going to plug everything in. My OH is 2.5 times 10 to the negative 5th. And this equation is on your formula chart in case you can't remember it for some reason. You can't remember the KW, you can find it. So that's basically it, guys. It's just using that equation to go back and forth between hydrogen and hydroxide.